Hey everybody, welcome back to another exciting lesson in calculus. Today we're going to take what we know about the derivative, just like always, at least for this semester, and relate it to something that's called related rates. Just like the idea of optimization, related rates is going to rely heavily on our understanding of geometry for the most part. Okay, and the idea of related rates is exactly what it sounds like. We know that the idea of the derivative is the rate at which things change. The related rates is the idea of relating that change. For example, I guess you could say there's a lot of different examples that you can say, but let's say we took a ruler or a ladder. A ladder would be a good example of this. If you had a ladder leaning up against a wall, and now the ladder is a fixed length. We're not changing the length of this ladder at all. But this ladder is leaning against this wall, and it's not set up right. There's no supports or anything below. It's not at a correct ratio, if you would. And so this ladder begins to slide down the wall. Well, as this ladder slides down the wall, what happens? Well, if this is the wall, it slides down the wall and it pushes the base of the ladder or the legs of the ladder out. And so maybe you have something that looks like this. Here's a wall, and obviously the ground, and then you have a ladder here. And this ladder begins to slide down the wall. So the top of the ladder moves downwards. Well, if this ladder is staying the same length, that would imply that this guy is moving out that way. So we have two different things changing. We have this length changing and this length changing. And the question for us is going to be, if we know how quickly one thing changes, what the rate is on one of them, then we can calculate the rate on the other guy. They are related to each other, and so that is what allows us to make that calculation. Okay. Ooh, my erasers are bad. So another classic example of this would be if I take a jug of milk. I don't know why I would do this, but if I take a jug of milk and I pour it out onto the counter, let's say, well, as I pour that milk, so here's I don't know, here's the flow, if you would, the stream of milk going down onto the counter, and as it hits the counter, you get a puddle, and as time goes on, that puddle gets bigger and bigger and bigger and bigger. So the puddle grows. So we can calculate the rate at which that puddle is growing in different ways. We can calculate it based on how quickly the radius is changing, how quickly the circumference is changing, how quickly the area is changing. But all three of those things are going to be related to each other. Okay, so that's the idea of related rates. We're going to spend the next, I believe, 4 lessons talking about this and going over a bunch of examples with it. So with that said, we got to take a step back and do a quick review, a quick reminder of the idea of implicit differentiation. Implicit differentiation, remember, is the idea that you're taking the derivative of not just variables, but you're taking derivatives of functions. So the derivative of a function, we'd say, is f prime, or we'd say df dx or dy dx, because x being our variable in that case. Okay, so remember, make sure to apply the chain rule. So I'll give you, I guess, an example here, or a few examples. What is the derivative of y in respect to x if we have 3xy equals y cubed? So remember, this is telling us that y is our function in respect to x, and x is our variable. So we needed to keep that in mind. So taking the derivative of this, I'm going to call 3x my first function and y my second function, or composition here. Not a composition, but product. So product rule, derivative of 3x is 3, then times y, plus derivative of y, which is y prime, times 3x. And then on this side, it would be 3y squared, but then we have to apply the chain rule, times the derivative of the inside, which would be y prime. And of course, y prime is just representing dy dx. And so we're trying to solve this. So we have to get y prime by itself. So I'm going to go ahead and move all the y primes to the right, just because I already have one over here. I got 3y squared times y prime minus y prime times 3x equals 3y. And then we're going to factor out the y prime. And then we're going to divide by that. So we get 3y over 3y squared minus 3x equals y prime. And we could reduce that to y over y squared minus x equals y prime, or equals dy dx. Okay, so that is an example of what this looks like. Make sure we are good here. Notice the way I did it here versus the way that's in the lesson. You'll notice the signs are completely different. You'll see in the lesson it says y prime is equal to negative y over x minus y squared. So you can see that it's actually equivalent. They're the same thing. There's a change in signs on the top and then a change in signs on the bottom. So really, again, when you're thinking about preparing for the AP exam and whatnot, if it's a multiple choice question and you get something like this, but you don't see your answer there, it may not be that you're wrong. It's just that you have to manipulate it algebraically to make it work or to make it match one of those answers. So in this case, if I multiply both the top and the bottom by -1 over -1, I'll end up with this. And that doesn't change the value of this, it just changes the look. Okay, so that is an example of implicit differentiation. Dy dx equals y over y squared minus x, and there's that one, right? Another way to look at this is to, instead of saying y prime, we'll call it dy dx. And that's going to be important for us when we talk about this idea of related rates. To understand that dy dx represents the derivative of y in respect to x. And you'll see more about that later. But the same work here, we isolated y prime, dy dx, and we solved it. All right. Now, let's talk about the idea of a function. Now, we know a function is a relationship between an input value and an output value. And sometimes we have equations that have multiple variables here. Now, this right here, a equals pi r squared, is not a function because we haven't identified what the input is and what the output is. Okay, it's not a function. Remember, it's the area, that's the area of a circle. But if I write it as a of r equals pi r squared, now it is a function. Well, what's the difference? Because now I'm clearly defining that a is the function, it's the output value, and r is the input, it's the variable. Okay, and that's important. Or this could be a function. A of t equals pi r of t squared. Well, it's actually not a function, it's multivariable. It's got multiple functions really in the equation here. Notice that a of t is a function of time, as well as r of t. R of t is a function of time. And so this relates, this actually corresponds with the example I gave about pouring the milk out onto the counter. You're going to get this circle that keeps getting bigger and bigger and bigger and bigger. Well, what's changing? The area is changing and the radius is changing. Now, we could say that the area is changing because the radius is changing, but really we could also go all the way back and say the radius is changing because of how much time I am pouring the milk, and the area is also changing because of how much time I'm pouring the milk. So I can create that equation that says area is in respect to time, and so is radius respect to time, okay? And that's going to be important for our lesson here. Here's another one, x squared plus y squared equals z squared. This is the Pythagorean theorem, obviously. It's not a function, though, because in this case, we don't have an identified input and output values. But if I write it like this, x of t equals, or x of t squared plus y of t squared equals z of t squared, now we're saying that x, y, and z are all functions of time. And so if I look at this, x squared plus y squared equals z squared, what we did in geometry is we just explored the static relationship between these three values. How is this related to these two things? But now we're going to be talking about how are these things related as, let's say, as time goes on, and we know that this length is getting bigger as time goes on, and maybe this length is getting shorter as time goes on. It still has the Pythagorean theorem in it, but it's not a static triangle. You're getting a triangle that's changing over time. Okay, and that's important to note, that we have multiple functions, I guess would be a better way of saying this, multiple functions in the same equation that are all related to t. The idea of a parametric equation is is exactly that. You have multiple functions related to a single variable, an independent variable, and that's called the parameter. The independent variable is called a parameter. Now, in Calculus 2, you're going to go a lot more in depth of dealing with parametric functions, but for now, we're just going to use them in a basic sense in related rates. Okay. So let's go ahead and take a look at an example. And this example at first is going to seem very simple. It's going to seem very obvious, but there's an underlying principle that we need to understand why this is true. Okay. So here it says if Bob heads north traveling 5 miles per hour and Larry goes south traveling 8 miles per hour, so Bob's going this way and Larry's going that way, how fast are they moving away from each other? And you might say, well, that's obvious. That's an obvious answer. Duh, it's 13 miles per hour. If this guy's going 5 miles per hour north and this guy's going 8 miles per hour south, they're moving away from each other at a rate of 13 miles per hour. But why is that? Well, if they're starting at the same place and Bob is heading that way, okay, we're going to say that the distance that he travels, we'll call B of t, right? The distance that he travels is related to how much time has gone by. And then who's the other guy? Larry goes down south at some rate of a rate of 8 miles per hour. So L represents the distance that Larry has traveled. Now, the equation that we can write here is we can say that wherever they end up, we can create a static equation, if you would. This whole distance, call it d of t, we can write this equation. B of t plus L of t equals d of t. That's the segment addition postulate. One piece plus another piece equals the whole piece. Now, this is a static thing. But as this gets bigger, as B gets bigger and L gets bigger, D will also get bigger. So it's not static. It keeps going over time. That's why I put the arrows there. Now, notice I said B is the distance that they've traveled, L is the distance that Larry traveled, and D is the total distance between them. The question, though, is how fast are they moving apart? How fast are they moving away from each other? Well, this doesn't deal with the rates. That's where calculus comes in. This deals with just how far apart they are. How do I get to the rate at which they move? That's taking the derivative, okay? So I notice that Bob is traveling at a rate of 5 miles per hour. 5 miles per hour. Well, how can I express that? That is B prime of t is 5 miles per hour. T as in time is the input, hours, right? And miles is the output for B of t. Therefore, B prime is going to be 5 miles per hour. And then L prime is going to be, what was it? It was 8 miles per hour. Again, I know this problem is basic. It's easy, just add them up. But I want you to see why this is happening, okay? Now, I need to create an equation so that I can find how fast they are moving away from each other. Well, the total distance represents how far apart they are. So that means I would want to figure out what d prime of t is. D prime of t, that's the question, okay? And so how do I get there? Well, I take the derivative in respect to time. You can see the variable's time here. You can see that underneath, miles per hour, we're talking about time. So time is our variable. B, L, and D are all functions of time. So what's the derivative of B of t? Well, that's B prime of t. What's the derivative of L of t? That's L prime of t. And what's the derivative of D of t? That's D prime of t. And then we can take, now we have rates, we can take those and plug them in now. So that'd be 5 plus 8 equals d prime of t, and obviously that's going to be 13. So d prime of t equals 13. You could have also written it like this. Instead of b prime, you could have said db in respect to time, dl in respect to time equals d of capital D, total distance, in respect to time. Okay, so that is the basic example of related rates. As one function changes, it affects the entirety of the rest of that equation. Okay, so let's kind of scramble through that and get that done. Okay, I like this. D of t equals B of t plus L of t is just a distance relationships. But we're talking about rates, and this is a good way to think about this, right? We're talking about rates. So what do? we differentiate, right? Rates, differentiate, it rhymes, it's good, right? But the rate of something is always dealing with the derivative, okay? So we take the derivative, d prime of t equals b prime of t plus l prime of t, and then we can plug those rates in and we get our answer. Now, I changed the question. Let me go back so you guys can see what changed between the two questions. Well, you'll notice it says Bob is still heading north. Bob is still heading north. But now Larry is not heading south. He's heading east. Which way is east? East is that way, okay? So now we've got to draw a separate picture. We've got to draw something else going on here. So we know they start at the same place, and Bob is heading north. So this distance is still b of t. Larry is heading east, so he's going this way. That's interesting. The question is, how fast are they moving away from each other? We're no longer counting this length or the total length between them added up. When I say how fast are they moving away from each other, I'm talking about this length. I'm talking about the hypotenuse. I could draw a straight dotted line there. Okay, so now this is the distance between them. How far am I from somebody? If I'm moving opposite directions, I would just add the two distances between them. But when one person's going one way and another person's going in a different direction, not the opposite direction, but in a different direction, the distance between them is the shortest distance being a straight line between them. Okay, so now identifying the things that are given, again, we know that dB dt is equal to 5, and we know that dl dt is equal to 8, and we are looking for dd dt. That's the question, okay? So now we need to create an equation that has all of these things in it. But don't be so quick to assume that, well, then you just say 5 squared plus 8 squared equals d of t, ddd of dt squared. No, that doesn't work, because this is dealing with rates. We don't have a Pythagorean theorem for rates. We have a Pythagorean theorem for length. So we first have to start off with a relationship dealing with length. So we would say b squared plus l squared equals d squared. That's obvious. This is the lengths, right? Now, we need to be able to take the derivative, because taking the derivative here gives us the dB dt that we want. Keep in mind that b, l, and d are all functions of time. It might have been better for me to say b of t squared plus l of t squared equals d of t squared, so we can see it. But I don't want to keep carrying down that t, because it's going to cause just chaos in our work. So just keep in mind b, l, and d are all functions of time. So taking the derivative of this, we would get 2b times b prime, because b is a function of time. So we have to apply the chain rule, where b is on the inside. The derivative of that would be 2b, and then times the derivative of the inside thing, that'd be b prime. Okay. Same thing here. L is a function of time, so the derivative of this would be 2l times l prime. And then over here, the derivative of this is 2d times d prime. So now I have a function, an equation, a relationship somehow, that relates my rates together, okay? Now maybe I can plug things in and see what I end up with. Well, I've got 2b times b prime. B prime is 5, so I'll plug that in, plus 2l times l prime, which is 8, and then 2d times d prime. And the question is, what is d prime? But we notice that we have a problem here. We don't have enough information to be able to solve for d prime. It doesn't work the way we want it to. So we need more information in this particular case, where in the previous one we didn't need that information. Here we do. Okay, so again, the scenario has changed. We're talking about them moving in different directions here. So b squared plus l squared equals d squared. Simplify the function, but remember all functions are in respect to time. So instead of writing b of t, we're just going to put b squared plus l squared equals d squared. take the derivative implicitly, and then plug in what we know. But again, even if we simplify this, like I did on the lesson here, we notice that we have a problem. There's not enough information. Okay, so let me add some more information. After 2 hours. After 2 hours. Let's add that. After 2 hours. How does that help? Well, I need to know a B. I need to know how far Bob is from where he started, and I need to know how far Larry is from where he started. So if after 2 hours they're traveling at this rate, we could say B of 2 is going to be 10. You go, well, how'd you get that? Because remember the dirt formula. Distance equals rate times time, right? B represents the distance. B of t is going to be equal to the rate of how fast Bob's traveling times the time. And that kind of makes sense. Rate times time. So B of 2 is equal to 5 times 2, which is 10, right? Now, dB dt is a constant here. That's why I'm allowed to do that. But anyways, I know after 2 hours, Bob is 10 miles from his starting point. B of 2 is 10. We could do the same thing on L. On Larry, L of 2 is going to end up being 16 because 8 miles per hour times 2 hours. So we can plug those things in here. That'd be 2 times 10, and then times the 5, plus 2 times the 16 times the 8 equals, but we still are missing D. Well, I can find this actual distance because now I know these distances. So we could just use the normal Pythagorean theorem here. We can say 10 squared plus 16 squared equals D squared. So that's 100 plus, I believe that's 256. So that's 356. And we'll square root it. So D equals, I don't remember what that is. Let's go ahead and cheat a little bit here. So we end up with 18.870. So you got a calculator, hopefully. Okay. And so now I can take that and plug that into D here. So 2 times 18.870 times D prime. And now it's just a simple equation that we can solve for D prime. So that would be 100 plus whatever that is equals 37 point something times D prime. And we can get our answer pretty simply from that, I believe. Okay. So we after we solve that, you can see that it says D prime is equal to 9.434 miles per hour. Well, what does that mean? He's traveling at 5 miles per hour. He's traveling at 8 miles per hour. They're not going to be traveling at a rate of 13 miles per hour away from each other, because that would be if they're directly opposite to each other. But because they're not moving directly opposite, you would assume that that rate would be less than just the sum of the two rates, and that makes sense. Okay, so hopefully that makes sense to you. Hopefully you get that. Let's go ahead and look at some more practice here. In this one, I'm not actually asking you to solve anything specifically, but just to create the equation of this relationship. It says, what is an equation that relates dV dt and dr dt for the volume of a sphere? Volume of a sphere. Well, you're going to have to go way back there and kind of remember the volume of a sphere. Sphere, remember, is a ball, right? Sphere is a ball there. That's a crooked ball, but that's okay. As time goes on, if we were to make this ball bigger and bigger and bigger and bigger, the only relationship you have geometrically is the radius to the volume. So the volume stands to reason that it will be, there'll only be one variable, and that would be the radius here. But if you remember, the volume of a sphere is 4/3 pi r cubed. So that's the equation that relates volume. But notice what I want here. I want an equation that relates dV dt and dr dt. That means I need to treat t as my variable, and I need to treat v and r both as functions of time. So think of v as a function, think of r as a function. both in respect to time. So now when I go to take this derivative, what's the derivative of v? That would be v prime. What's the derivative of the right-hand side? Well, 4/3 pi r cubed. Pi is a constant. Power rule here, we're going to end up with 4 pi r squared, and then times the derivative of the inside thing, which is r prime. And so we end up with, and I'll just rewrite this, v prime can be rewritten as dv dt equals 4 pi r squared times dr dt. Interesting. Very interesting. That should make you go, wow. If you're not going, wow, then you're missing something here. Why? Well, let's go back to the area of a circle. And let's just think where r is the variable. Okay? Let's treat r as the variable in both these cases. So not time, but just r. What's the derivative of a in respect to r? Well, that would be 2 pi r. What's the derivative of volume in respect to r? That'd be dv dr is equal to 4 pi r squared. And I don't have to say times r prime in either one of these because r is the variable in this case. So if I want to use the chain rule, what's the derivative of r? The derivative of r is 1. Okay. Now this, you should see the connection here. Isn't it amazing? It should just blow your mind that the derivative of an area equation is the circumference of that circle. If the area of a circle is pi r squared, then the derivative of that area in respect to r is the circumference of that same circle. Here, look at this. You may not see this directly, but this is the volume of a sphere. The derivative of the volume of the sphere in respect to r is, what is this equation? That's the surface area of the sphere. It's crazy to think about. That relationship is there. That the derivative of area is circumference, and the derivative of volume is surface area. That's kind of cool. Now, that's just a side note because that wasn't the question here. But here is an equation that relates dv dt to dr dt. Okay, so that's pretty straightforward. All right, with that said, let's go ahead and look at one more example. It says relate dv dt, dr dt, and dh dt to the volume of a cone. Volume of a cone. Well, what's a cone? Here, I'll do an upside down cone because it's just easier to draw. Okay. I have a cone here. What are the things that change the volume? Well, how big the radius is going to change the volume, and then how big the height will change the volume. And it says we want to write an equation that relates dv dt, dr dt, and dh dt. So volume, radius, time. Well, what's the volume of a cone? The volume of a cone, if you remember, is the same as the volume of a cylinder, but it's 1/3 of it. So the volume of a cone is 1/3 pi r squared times h. Pi r squared, the area of the circle, times the height, gives you the volume of the cylinder, and then we divide it by 3 to get the cone. All right, well, v, r, and h are all functions of time, so keep that in mind. Taking the derivative of this, the derivative of v in respect to t is dv dt. The derivative of this side, well, I'm going to treat 1/3 pi r squared as one of the functions and h as the other. So that's going to be 2/3 pi r, 2/3 pi r times r prime times h, because I'm using a product rule, plus h prime times 1/3 pi r squared. And I'm running out of room here, so hopefully that's all there. That's all there. Okay. So that is the relationship, and I'm mixing up my notation here. Leibniz form, Newton's form. So let me rewrite this. dv dt is equal to 2/3 pi r times dr dt times h plus dh dt times 1/3 pi r squared. And then we could probably simplify that a little bit, put that coefficient out front there. That should be an r. Maybe you could factor something out, I don't know. But that is the relationship between all of that. So the first step in all of this is creating the equation that you can work with. Okay, so just like always, maybe draw a picture, create the equation that it's asking you about, and then take the derivative in respect to time. All right, so there we go. Let's go ahead and take a look at one more example. I like this example because it deals with, I don't know if you've ever watched a hot air balloon take off. I've had the opportunity to see it a couple times. It's kind of neat. I guess I'll tell you a little bit of a story. We were in Utah a few years ago, and we were watching a hot air balloon launch, and we were pulling up to the area, and where you're supposed to where we see all these hot air balloons off in a field, and they're getting ready to blow up the hot air balloons and take off and everything. And so we just turned down. We saw them. We turned down and down this dirt road, and we started just following the trail until we got to where everybody was. And we parked, and we put down the tailgate, and we're just sitting there watching and everything. And this guy, this hot air balloon guy, starts blowing up his hot air balloon within 20 feet of our truck. And I go, oh, that's kind of cool. But if you know hot air balloons, you can't really control where they're going. The wind is going to control them. And so, he gets the hot air balloon off the ground, and it starts going up, and then they start taking off. And quite literally, I had my tailgate down and the back of my camper shell up, and he's yelling from up above. He goes, "You got to put your camper shell down, lid down, because I'm going to hit it." And literally, I had to put it down, and he missed my truck by just a couple feet. Well, I found out later that we parked in the wrong spot. Spectators weren't supposed to park there. It was only the people with the hot air balloons that were supposed to park in that area. So we had up front, close seats, and nobody said anything, so it was just a good experience. But anyways, that was a waste of time, other than a good story. A hot air balloon rising up from the ground is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4 angles here. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So we're going to want to draw a picture here. So here is my hot air balloon, right? Here's my hot air balloon. It's going to be an ugly hot air balloon, but let's say it's something like that, right? And here's the guy over here with the rangefinder. So this is the rangefinder. Now, we're going to be measuring from the base of the hot air balloon, okay? So we know that the rangefinder is 500 feet away from the hot air balloon at takeoff. Now, if everything is done right, we know that this hot air balloon is going up into the air. So this guy is heading upwards. And so let's call this the hot air balloon, right? There's the hot air balloon now. It's heading upwards. Now, assuming that it goes up at a right angle, it doesn't. According to my story, it doesn't, because he took off here and he just barely missed my truck. But we're going to assume that it goes straight up. Now, this rangefinder is 500 feet away, and it's trying to figure out the distance between it and the balloon. Now, it says that the rangefinder's elevation angle, remember, angle of elevation, is the angle formed by a horizontal line and the line of sight. So this rangefinder is looking up at this balloon, and we know that this guy is going to be pi over 4 radians at the moment that we're asking this question. Okay, so here's the picture. It's important that we identify the things that are changing. So maybe I just draw the picture here for right now, and we put variables in place. We'll call this theta to represent the angle. We'll call this the height of the balloon, so we'll call that h. We'll call this the, r for the distance to the rangefinder. And then we'll call this d for the distance between the rangefinder and the balloon. Now, we have to ask ourselves, what components are changing here? Well, here, as the balloon rises, obviously the height is changing. Is r changing? Well, no, r is not changing. The distance between the rangefinder and where the balloon took off is staying the same. The rangefinder isn't moving back and forth, it's staying the same. Well, is the angle changing? Yes, the angle is changing. The angle is increasing as the balloon goes up. Is the distance between the rangefinder and the balloon changing? Well, yeah, as that goes up, it's getting longer. So we have three things that I've identified here that are changing: theta, d, and h. But r is a constant. R is a constant, and that's important. Now, the question is, how fast is the balloon rising at that moment? So let's go back and read the pieces, and we're gonna write them down off to the side. Okay. The first thing is, it says that the rangefinder is 500 feet away. So R is 500. Okay. And remember, I said that that is a constant. That's constant. That's not changing. And then it says that at the moment, the rangefinder's elevation angle is pi over 4. So theta is pi over 4. And that's not constant. That's changing. The angle is increasing at a rate of 0.14 radians per minute. Well, how do I write that down? The angle is increasing at a rate of, well, that is d theta dt. The angle is increasing at a rate, there's your rate, of 0.14 radians per minute. And so you can see it there. Minute is a time, radians is our function here. So d theta dt is 0.14. How fast is the balloon rising at that moment? So how fast is the balloon rising? Well, h represents where it's at. How fast is it rising? That would be dh dt, right? That's, again, a rate. So the question is, in this case, dh dt. So we've got to figure out an equation for dh dt that relates all of it to what's given here. So we need an equation with h in it, an equation with theta in it, an equation with r in it. And I don't see any need for d, at least not yet. Somebody might say, well, let's do the Pythagorean theorem. You could, but that's gonna put in d, a variable d that's not given, and it's going to take away from the variable that is given. So maybe we should just ignore d. Okay. So what's the equation between these three things? Well, that should be easy. That's going to be the tangent of theta is equal to h over r, opposite over adjacent. So there is my equation. Now, how do I deal with this? Well, there's a couple different ways to approach this. I want dh dt, so I have to take the derivative of h, first of all, as a function. And I have d theta dt, so I have to take the derivative of that as well. So let's go ahead and just take the derivative of this. The derivative of tangent theta is going to be secant squared theta times theta prime, or d theta dt. On this side, we can apply the quotient rule, but here's where it gets interesting, because remember what r is. R is a constant. So h, the derivative of h would be h prime times r minus the derivative of r prime. What is the rate at which r is changing? I didn't write that down. I don't have that over here. I could say r prime times h over r squared. I'll go ahead and do that for now. And now let's see if I can just plug in anything, plug in all the stuff here. Well, I've got secant squared of theta. Theta was pi over 4 times theta prime. Oops, I know what theta prime is. Times 0.14 equals h prime. I don't know. That's what I'm looking for. Times r. R was 500. And then minus r prime. I didn't give you r prime. But remember, r is a constant. So the question is, how quickly is r changing? What is the rate at which r is changing? R is not changing. R is constant. So therefore, the derivative is 0. We could write this down as a result of this, that dr dt is 0, right? The derivative of a constant is 0. And then times height times h. Well, I don't know what h is, so I'm going to go ahead and write that down here. Over r squared. R is 500 again. So 500 squared. And so again, remember, we are looking for h prime. And as much as we can simplify this, we still have h left over. So we're going to have to figure out something else for h. Well, fortunately, we can go back to our original equation and say, well, the tangent of pi over 4 is equal to h, which I don't know, over r, which is 500. And so the tangent of pi over 4, that's just going to be 1 equals h over 500. So h is 500. Is that correct? I believe that's correct. So h is going to be 500 here. But oh, maybe you caught this. I don't even need that because I got 0 times h. I didn't even need to figure that out because that's all going to go away. Anyways, secant of pi over 4, that's the reciprocal cosine of pi over 4. That's going to be 2 over rad 2 squared times 0.14 equals, and I'll simplify this side to be, I should probably make some room here. Let me put that up here. Just carry it over here. So that's going to be 2 over rad 2 squared times 0.14 equals, that's all going to be 0. One of the 500 is going to reduce, so we're going to be left with h prime over 500. And then simplifying this from here, I'm not going to spend all that time simplifying it. The answer is going to be 140 feet per minute. H prime equals 140. And because h is in respect to, or h is a foot because r was feet, right? This would be feet per, and then the time element was minutes. Feet per minute. 140 feet per minute. All right. Now, I wanted to explore this a little bit more. I want you guys to understand the importance of when you should plug numbers in. We are not dealing with static information. We're not looking at a picture, a diagram, and saying, let's figure out information about this diagram or this moment in time. Okay? We're not looking, it's not like we're going outside and saying, okay, let's create a math problem. So I'm going to take a picture of this math problem, this situation, and measure those things and calculate those things. No, we're talking about movement here. So instead of taking a picture, it's like watching a movie. We're watching this play out. And as a result of that, you have to be very careful when you plug numbers into your equations. Because if you plug numbers in too soon, then what you end up with is constants. If you plug numbers in, you're implying that those things are constant values, okay? So what we want to do is always take the derivative before we substitute, because all this information, not the top one because that's a constant, but all this information is changing. And I am asking you to find information at a split second in time, at a specific moment. So once you have your equation, do not plug things in. Because, for example, if I were to plug in pi over 4 right here and then take the derivative, well, let me write that down. If I have the tangent of pi over 4 and then I take the derivative of that, notice that this is a constant. This is a constant. What's the derivative of a constant? It's 0. If I plug in a number before I take the derivative, then I'm saying that that number is not changing, and therefore the rate is 0. But that's not the case here. We have rates. We have values for rates, so things are changing. My point is, do not plug anything in until after you take the derivative. There is one exception to that, and that exception is if a value is a constant value, you know it's not changing, well then when I take the derivative of that constant value, I'm going to end up with 0 anyways. So I can actually rework this problem probably a little bit quicker, because I recognized that r is a constant. So I'm allowed to plug that in early. I'm allowed to plug that in before I take the derivative, because that's not changing, okay? So when I go to take the derivative of this now, I end up with secant squared theta times theta prime equals, and then the derivative of this, well, that could be rewritten as 1 over 500 times h. So the derivative of that would be 1 over 500 times h prime. And so it makes the problem a lot easier to look at. Sorry, theta prime there. And then plugging that in, we get secant squared theta. That'd be 2 over rad 2 because we did the work on that earlier. And then square it. Theta prime is 0.14. And then 1 over 500 multiplied by 500, you end up with the same exact thing. It's just a little bit quicker. But you cannot do that unless the thing that you're plugging in is a constant. If it's not a constant, if it's something that's changing, make sure you take the derivative before you substitute. That's where I'm going to leave this. That's the end of this lesson. Hopefully you get it. Hopefully you understand it. If you have any questions, please comment below, and I will answer those for you. And I will see you again next time.